Hey, hello physical science, this is Mr. B, and we are going to wrap up section 3 today with Newton's third law of motion and momentum, and we're really going to focus on momentum. And if you remember, Newton's third law says that objects exert equal and opposite forces on one another, kind of paraphrasing there, and that applies to momentum. And we're really going, and momentum, remember, is mass times velocity, and we're going to really look at how those two things intertwine today when we talk about how momentum is conserved. So we're going to talk about different collisions that occur between two different objects and how momentum is actually conserved. But first, before we talk about momentum being conserved, you're going to hear the term a closed system. So when we talk about a closed system, that means other objects and forces cannot enter or leave a system. So it's basically having something that occurs, kind of almost another way to say it is almost inside a vacuum, where no outside forces can act on anything that's going on inside of our specific example, and then no force is ever going to leave our example. So when we look at our example, it's isolated with nothing else acting on it. Nothing can leave. Basically, nothing can really affect our calculations besides what's actually going on. So no friction, no other outside forces. So we're going to focus on a closed system today. So in a closed system, the loss of momentum of one object equals the gain in momentum of another object, and therefore momentum is conserved. So this is where Newton's third law kind of comes in with the equal and opposite reactions on one another. So when we're talking about a closed system, if one object loses momentum, that means that another object is going to gain the momentum from that object. So momentum is never lost, it's never created, it's never going to be destroyed, it's conserved, it's going to be passed on from one object to another. So objects within a closed force can exert forces on objects within a closed system can exert forces on one another, and according to the law of conservation of momentum, if no net force acts on a system, then the total momentum of the system does not change. So in a closed system, that means, again, it's kind of almost just like an isolated system, that nothing else is going to come act upon any of the objects that we are studying. The total momentum is never going to change. It's always conserved when we have it isolated inside of a vacuum with nothing else coming in. Again, in real life situations, it's hard to come up with a closed system because there's always some type of friction, always some type of thing acting upon it. But for our law of conservation of momentum, we are speaking in a closed system with nothing else acting upon what we're studying, so therefore the momentum is never going to change. So we're going to see a couple examples. We're going to have several collisions, and you're going to notice in each collision the total momentum of the train cars does not change. The momentum is conserved. So if you look, we have 10 meters per second, 5 meters per second. The momentum is 300,000 here, 150,000 here. So our momentum before the collision, if you add these together, is 450,000. And then the two cars are going to bounce off of one another. And then now the momentum of this car is 5 meters per second and 150,000. And now our second car is 10 meters per second with 300,000 momentum, and you notice that it is now equal. Everything is equal before and after. The momentum was conserved, it was transferred from one car to the next, and that's what we're going to see in this example as well. This car, only one car is moving, and then again in a closed system with no other forces, when this single moving car bounces off the one, all of the momentum from the moving car is now transferred to the non-moving car, and our momentum is the same before and after the collision again as well. And then now one car is moving, and then the cars are going to actually not bump off of one another, but they're actually going to hook up and form one, so the cars are going to couple. So even when they're not actually bouncing off one another, when the cars, again, train cars are actually meant to stick together. So in a real life situation, if the train cars stick together, our total momentum is still going to be the same, because now we have one object with in that same momentum here. So momentum is always conserved when we're in a closed system, when there's no other forces acting upon it, and that really directly applies to Newton's third law when it talks about equal and opposite forces being exerted on one another. This is a perfect example right here. Momentum in a closed system is basically the perfect illustration of Newton's third law. And so to wrap up this section, we're going to take a look at some graphing of momentum, because graphs are pretty important to know how to understand and kind of make some inferences from, because you guys are going to be tested on that quite a bit. So the example we have here says a class studied the speed and momentum of a 0.25 kilogram ball dropped from a bridge, and the graph shows the momentum of the ball from the time it was dropped until the time it hit the river flowing below the bridge. So we have a little graph here, and hopefully we can maybe figure out the answers to these questions. And you know what? I'm going to actually maybe give some extra credit if you can figure out the answers of these questions based off of what the graph says. So it says, at what time did the ball have zero momentum? And then describe this point in the ball's motion. So by looking at this chart, at what time did the ball have zero momentum? And then what was the ball's motion like when it had zero momentum? So that's the first question. Again, I have the answers over here, but I'm going to try to skip over them so I don't give them away to you. And then our next one, at what time did the ball have the greatest momentum? And so again, what time down here was the greatest momentum, and what was the peak momentum value? So what was the value of the momentum there? And then for our last one, what is the ball's speed after 1.25 seconds? And so it says to use the graph and the momentum formula. Again, remember our momentum formula is mass times velocity. So our mass is right here, and we might know our momentum right here. So we're just going to maybe plug in some different values to figure out what our velocity would be. Again, figure those problems out. Again, you can earn several extra credit points this way. I know a couple of you have been asking ways to earn extra credit points. So as a reward to those actually listening to the video, there's 3 different problems, and again, depending on how many people answer those 3 questions correctly, we can get you some extra credit. So that is it for section 3. Let me know if you have any questions.